So now we're going to go from regression to classification, and we're going to do classification with something called logistic regression, which is actually a regression. This seems a bit confusing, but it's a good way of understanding exactly what is the difference between regression and classification. So I'm going to give a brief introduction to the idea of classification and separability, in particular linear separability, because logistic regression is also a linear model. And then we're going to look at logistic regression and do something similar to what we saw last week with linear regression, which is how we can increase the power of the model by going to higher dimensions with nonlinear transformations. So first, this notion of separability. The idea is that we have two classes in this example. These are gene activities measured on cells, and we have in red cells that belong to tumors and in blue cells that are normal. And we say that these classes in this data set are linearly separable because we can draw a straight line, or if we were to generalize for higher dimensions, a hyperplane that can separate the two classes. So we can separate the two classes linearly. They are linearly separable. We call this frontier the discriminant, which is what separates the two classes. And in this case, it's a linear discriminant. It's a straight line. If the classes are distributed in a different way, for example, this is the same set of cells, tumor and normal, but using different gene activities, and we see that the blue ones come here, and then there are the red ones there, and there is no straight line that we can draw to separate the two sets. So these are no longer linearly separable, at least in this representation. So now the problem of classification is we want to find the discriminant that separates the two classes. Let's suppose that we are dealing with linear discriminants here, so we want to find something straight, a line, a plane, a hyperplane that separates the two classes. When we were doing linear regression, we defined the line this way because all we wanted was the actual line that was going through the points. In classification, we need to have an idea of what is to one side of the line and what is to the other side of the line. So it's not sufficient that we draw this line. We need to be able to distinguish this side from this side and know which side belongs to which class. So one way of representing the discriminant, a linear discriminant, we can represent like this by using one vector that is perpendicular to the plane and is pointing to one of the classes. So this would be the positive class. What is on the other side would be the negative class. The plane would be all the points that lie on vectors that are perpendicular to the vector that defines this plane. So we can do that by computing the inner product, and we have a 0, and this constant determines whether the plane is higher or lower. So this would be one representation. If we had the problem in 3 dimensions, we could specify the orientation of this plane with this vector. This vector here would point to the positive class, and on the other side would be the negative class. So this way we can separate the classes, and we know which side belongs to each of the labels. So the problem now is, how do we find the discriminant? We know how to define the discriminant. We have this vector and this constant, and the discriminant is the plane where we set that function to 0. So this function here, using that perpendicular vector and that constant, will be positive on one side of the plane, negative on the other, and we can decide that we want to split things at 0, which is the position of the plane. But the question is, how, given the data, how do we find the parameters to place the discriminant in the right place? So let's start by doing this incorrectly. We're going to use the same thing that we used for regression. So the idea was that with regression, we were minimizing the quadratic error, and so trying to fit the line to the points. In this case, we can say that on one side of the discriminant, the points belong to class 1, on the other to class -1, and we have this function that is positive on one side and negative on the other. So we could try to fit the discriminant in a way to minimize the error between the class labels that we're trying to predict and what the function is gives us, so that we place the discriminant in a way that is positive on the class +1 and negative on class -1. So we're going to do this the wrong way because I want you to understand why it's wrong to do it this way and why we need to do something different for classification. So let's do the same thing, minimizing the quadratic error. This is the difference between the predicted value and the true value, which is 1 plus 1 for one class, minus 1 for the other. So let's start with this data set here, this one. We have these columns here. These are the two relative gene activities, and then we have the class, 1 for the tumor, 0 for normal. So we're going to rescale everything. And now I'm going to show you two different ways of rescaling. Normalization, also called max-min rescaling, takes a set of values and rescales everything to fall between 0 and 1. So for each value, we subtract the minimum of the set and then divide by the difference between the maximum and the minimum. So everything will be shifted and rescaled to fall between 0 and 1. Standardization takes a set of values and rescales that set in order to give us a distribution with a mean of 0 and a variance of 1. So this would be, we would, for each value, subtract the mean or the average of all the values, and then divide by the standard deviation of the original set. So these are two ways of rescaling. This one puts everything between 0 and 1. This one puts everything in a distribution that is close to 0 with a standard deviation of 1. So basically, if you have values that have a normal distribution, standardization is very good because it puts everything neatly there. Or if you have some outliers or something like that, standardization works better. If you have something that has some fixed range, then usually normalization can work better because it sorts things out a bit better. One important thing, regardless of how you rescale your data, the parameters that you compute here, these minimum, averages, standard deviation, so on, you need to keep them and then use always the same parameters for new points. Because otherwise everything will go wrong. If you compute the parameters for the training set and then compute new parameters for new points that you are observing, then you will get everything out of scale and it won't work. So we are not going to worry too much about these details, at least in the lectures, because we're going to look at fundamentals. But in this case, it's important that you remember that the parameters that you use for rescaling, you store them and use them consistently in all points that you examine later. So we're going to load this data set, this text file here, and now we're going to extract the class label. This is the last column of the matrix, and this is one of those other details that you can do in Python with these matrices. If I just choose the last column, I will get a vector which has a dimension of 1. It's just a linear vector. But if I choose a set formed by the last column, so by using those square brackets to indicate a list, then I get a two-dimensional matrix with only one column, which is a different kind of object. So if you want to preserve the dimensions, you can do it like this. If you don't care, then you don't need that. In any case, we are separating the y values, because the y values are the class labels, and we are separating that from the x vectors, which are these pairs of values for each point. And now we're going to standardize the x values. Note that we are doing this because it's not reasonable to standardize the class labels. The class labels are just zeros and ones. We don't want to rescale anything that. We only want to rescale the features, which are the input values.
Yeah. If we do the min-max normalization, and in the test or validation I have some values after, so I don't have all the data between 0 and 1.
Mm-hmm.
So there is a way to have all the
No, because even if you can do this for your whole data set, but then if you find new points in the future, you cannot guarantee they will fall between that range. There are some cases where you can. For example, suppose that you're dealing with images and you know that each pixel ranges from 0 to 255, something like that. But in general, you cannot guarantee that. However, that is not very critical, because the reason for doing this is to avoid numerical problems during training of your model, and also so that you can have an idea of what the range of hyperparameters would be, and so on. If you change too much the scale, then you cannot do that. But after everything is done, if there is one data point that falls slightly outside, that should not be critical, okay? Because you already have everything set up. Yeah, in case of the images, you could use 255 that and rescale everything. So, but those are special cases. In general, you cannot guarantee that. So now I'm just going to do a simplification here on the notation, because we have been considering a vector of parameters, and this is a bit awkward because we have one vector here plus another scalar there. So let's put everything together, and we can do this if we imagine that we add another feature to the x value, which has always the value of 1, and we include this w0 on our vector. In that case, we can just multiply this expanded w, which has all the values of w plus w0, multiplied by the x, which also has an additional 1 everywhere. So if we do the inner product of these vectors, it's the same as doing that over there. And it simplifies the notation, and it can also simplify the code if you do that, because you don't need to keep adding and having one parameter that is outside the vector and so forth. So to do this, to add one feature that is all at once, so this would be a dummy feature just for the computation, all we need to do is to create a new matrix filled with 1. So this 1 function creates an array filled with 1 that has the same number of rows as the original X matrix, but has one additional column. And then we copy the original values for the all rows except the last one. So now all our vectors have the original features plus a 1 at the end. And this way we can represent the parameters for the model as just a vector that we will multiply by the expanded data in this way. So now we can do, we can compute the, note by the way that you will not need to do this in practice, because when you start using this we will jump to the scikit-learn and use the logistic regression implemented there. But I'm just doing this step by step to show you how the algorithm would work, and also because we are doing the wrong answer first. So we have the data set up. Now we compute the cost function, that is the quadratic error. So we will multiply the coefficients vector by all the data. This will give us this y function here that is negative on one side, positive on the other. So we do that with the dot product there. In order to do this multiplication, we need to have this vector as a column, and this vector is a row. So we just need to do this reshaping here. So I create a matrix that has one column, and I copy the coefficients there to the column. But this is just to manipulate the vector so that we can do the dot product. And now we have the predicted value. So this dot product here is the dot product of the vector of the parameters of the model and all the examples that we are feeding for training. And now we subtract from this the class labels. One of them is -1, the other is 1. Now one thing that is important when you are dealing with classifiers is that some of them will presume that class labels are 1, -1, others would use 0 or 1, and you need to pay attention to that because it depends also on how it's labeled on your data set. So this, for example, in this case, our data set has labels 0, 1, but we are assuming that we want class -1 on the negative side and class 1 on the positive side. But it's easy to convert that by multiplying the class label by 2 and subtracting 1. So if the class label is 0, this is minus 1. If the class label is 1, this is 1. But this, the reason I'm putting this example here is that this is a common source of problems. Everything seems to be okay, but then the results don't make sense, and that's because you're using the wrong class labels for the classifier, what the classifier is expecting. So pay attention to this in practice. You don't need to do this, all these cost functions and so on in practice, but you need to pay attention to these details. Okay? So now we're going to minimize this quadratic error. We can use that with an optimization library. From SciPy, we can use this model, optimize. There is a minimization function that we can call, giving the function we want to minimize an initial guess for the parameters, but then the minimization function will change the parameters to try to find the smallest value. Additional arguments for our cost function, and then we can set the criteria for stopping so that tolerance determines when the minimization function stops. So basically we are minimizing this function here and trying to find the combination of coefficients, these values for the w, that gives us the smallest quadratic error. So this function y is positive on one side, negative on the other. We are comparing those values of y to the class labels 1 and minus 1 and minimizing the quadratic error. So we do this, we run, and we plot the chart, and this is what we get. So if we try to do this with a least mean squares minimization, we have negative on this side. The normal class is the minus 1 class, and it's trying to adjust to these minus 1 labels on the negative side, and positive over here, and these are the plus 1 labels here. But the problem is that the function is increasingly negative on this side and increasingly positive here, or the error, the quadratic error, will increase the more we go away from the discriminant. This is a good idea when we are doing a regression, because we want the line to pass close to the points, and if some point is far away, we want to move the line closer to the point. That's why we give a larger penalty to points that are far away. But it's not a good idea when we want to separate the points. It's obvious that the line should be here, but since there are points over there far away, and we're trying to minimize the quadratic error, those are pulling the line over there, and even leaving some on the wrong side here because they are far away. So this is one basic idea of the difference between regression and classification. In regression, we want the line to go close to the point, so we want to penalize things that are away from the line. But in classification, we don't care if points are far away from the line, as long as they are on the right side. So if we put the line here to separate the two classes, that's perfectly okay. They are on the correct side, so we don't worry about them. The problem is this part here. We want to separate the points correctly. So with the least mean squares, we are having this problem that we are pulling the discriminants towards points that are far away, even if they are on the correct side, and we should not bother with them. So this gives us this very important difference in that in regression we are trying to fit our model as close as possible to the data, whereas in classification we want to find a discriminant that splits the data in subsets that are correctly divided. Okay? So let's see how we can solve this with logistic regression. Let us assume that we have some function, g. We'll see how that function is, but this function gives us the probability of a point x belonging to class 1. So this is the conditional probability of the point belonging to class 1 if we know the features of the point. In our example, it would be knowing the gene activities, we would predict the probability of being a tumor. That would be class 1. So this would be a continuous function because it's the probability, and we're trying to find a function that approximates the actual probability of the point belonging to the class. And we want to set the discriminant, that hyperplane that separates the points, at the values where the probability of belonging to class 1 is the same as belonging to class 0. This intuitively, this is a bit arbitrary, and we'll see later on that we can change this criteria, but intuitively it means that on one side of the discriminant it's more probable that it belongs to class 0, on the other side it's more probable that the point belongs to class 1. This would be our estimated probability, and that's why we put the discriminant there. So, since the discriminant, we want it to be a linear discriminant, and we want to define it by that W vector, we can also do here a bit of a transformation by choosing this place, so this point for the discriminant where the probability of one class is the same as the other, but since probabilities go from 0 to 1, then it means that the probability of belonging to class 1 at this discriminant is 1 minus the probability of belonging to class 1, because this would be the probability of belonging to class 0. And we can, if these two are equal, then 1 over the other is 1, and we can take the logarithm of that to be 0. So the logarithm of 1 is 0. The reason why we're doing this transformation is because of the shape of the function we get later, but we can see it now. If this is our function, we don't know yet what our function would be, but we know that in this case, when this is 0, we are at the discriminant, and we know that we want the discriminant to be linear, to be this hyperplane defined in this way, or if we put this W0 there on the W, we do that expansion that we saw, we can simplify this and use only that W with the tilde. So if we solve this equation, we get this shape for our G function. Our G function will be 1 over 1 plus e raised to minus the expression for the function that defines that discriminant. Why is this function interesting? The reason for this manipulation is that this is the logistic function, and it varies smoothly from 0 to 1, which is really what we need for probabilities. If we want something that we can interpret as a probability, it should vary from 0 to 1. But it also has another interesting property, and is useful in this case, is that if you go to very negative values or very positive values, it stays either at 1 or at 0. It no longer increases. And the reason why this is useful is that it solves that problem of pulling the discriminant towards points that are far away, even if they are on the correct side. So the quadratic error function that we were using to try to fit our data was pulling the discriminant incorrectly, because it keeps increasing as we go away from the discriminant. If we use the logistic function, then things flatten out, and if the points are correctly on the right side of the discriminant, then it doesn't matter if they're far away or close by, they all count for the same. So we avoid that problem. So let's see how we can now find the best discriminant. Because we were using quadratic error to find the best parameters, now we have a completely different function here, and we need to see how we're going to optimize the parameters. But the idea is the same. Remember that we got the quadratic error, minimizing the quadratic error, by using this maximum likelihood principle. We want to adjust the parameters in a way that the estimated probability of the data is maximized. And the estimated probability of the data is the likelihood of the parameters that we are using in the model. So we want to maximize the probability of the data. That is, we want to maximize the likelihood of the parameters, and the probability of the data will be the estimated probability G for all those points that belong to class 1, because this is what our function is supposed to represent. Our function G is supposed to give us the probability, or an estimated probability, of belonging to class 1. So all those points that belong to class 1, we multiply the value that G is giving for those points. So this would be G raised to the class of the point. For the points that belong to class 0, we do not use this value. But then G raised to 0 is 1, so when we multiply, things work out fine. If the points belong to class 0, then the estimated probability of belonging to class 0 will be 1 minus G. because G is the probability of belonging to class 1. If we take 1 minus G, that's the probability of belonging to class 0. And now we raise that to 1 minus the class, because if it belongs to class 0, then this would be 1, and we use the actual value. If it's in class 1, then we ignore this part. So basically, we can see this expression, this product, as multiplying this part whenever we are in points of class 1, or this here if the points belong to class 0. So it's either one or the other, because otherwise that exponent there becomes 0, and we ignore that term. So this is the probability of all our data sets given some G with the right parameters W. And this is the likelihood of the parameter computed on that data set. We can take the logarithm of the likelihood. This is what we did last week too, because if we want to find the maximum of that value, we can also find the maximum of the logarithm, and it will be the same set of parameter values. So we take the logarithm, we do away with the products, and also those exponents there, we can get, and we find this expression here. So the class multiplied by the logarithm of the probability of belonging to that class, and plus 1 minus the class multiplied to the probability of belonging to the other class. So if this is actually called, this is actually a cross entropy when we do the, when we change the sign to minus and we do the average. This is cross entropy, or also called logistic loss because of this logistic function. And maximizing this is the same as minimizing this. We change the sign here. So this would be our error function. Our error function is no longer the least squares errors or the quadratic errors, but is this the cross entropy that we're going to try to minimize. So this, another important thing here is that we are using the same principle, trying to find the parameters that maximize the estimated probability of the data, that is maximum likelihood, but because our function is different, now we get a different cost function to minimize. Okay? But the principle from this more abstract perspective is the same as we saw last week. So this would be the function we want to minimize, and when we find the right parameters here, we obtain the this function, the hypothesis that we want, that gives us the probability of belonging to each class. Okay. So let's see one example where things are linearly separable, and once again I'm going to do this step by step with bits of code, but when you do use logistic regression, it's best just to use the logistic regression classifier that you have in scikit-learn. I'm going to show that one too. But this is the logistic function, so it's 1 over 1 plus e raised to minus x. Note the power here is the 2 multiplications in Python, so this is raised to something. You have the base of the natural numbers there in NumPy, and we're just computing this expression here. Now we create the logistic cost function to minimize. So basically, we're going to do these two products: the class multiplied by the logarithm of the estimated probability, and 1 minus the class multiplied by that one. But this, we only need to do this for class 1 and this for class 0, because otherwise we get 0, 0, 0s there, and those things, they won't make a difference. Okay? So we can do this like this. We can compute the logarithms of the values for the logistic function. We can add everything and take the mean. So basically, this is just creating, multiplying here the x by the parameters, then calling that function there to compute the value of the logistic function for all the points. So we do that here, and then we compute the logarithms for those of one class or the other, and then sum everything, or compute the mean and change the sign. So these 3 lines are basically doing this computation here. And this would be the cost function. We want to minimize that logistic loss, or the cross entropy in this case. And now we can, I'm omitting the code, but basically it's the same thing that we did here, which is to use the optimizer and do the minimization and get the parameter. So if we do this, even doing this by hand, we can see that now we get something that is a lot better. Because these points over here, even though they are far away from the discriminants, are no longer pooling everything there, because we have this function that behaves a lot better. This is a classifier because we are using this discriminant in the line where the probability estimated for one class is the same as the other, but it's actually a regression because what we're doing inside in the engine is trying to fit this G function that gives us the probability of belonging to a class. So the probability is this continuous value between 0 and 1, and we're trying to approximate the probability. But then we use the probability at 50% to cut off the two. Yeah. Okay. So in a linear regression, we were fitting a linear combination of values to try to approximate as much as possible our data points. In a logistic regression, we are fitting this logistic function to approximate as much as possible the probability of belonging to one class. So we're not approximating actually the data, we are approximating the probability of belonging to a class. When we then cut that function in the 50% one class, 50% for the other, we get something that is very different from a linear regression because it's not a line that goes through the points. For example, if we were to do a linear regression here, we would get a line more or less like this. This is a line that cuts the data into two subsets. So this is very different from regression. We are doing a regression for this, but doing a regression on the probability. But then we choose a cutoff point and we divide the set into those. No, clustering is very different because clustering is used when you don't know the labels for the classes. Okay? So this would be, you don't know which is blue and which is red, and you're trying to figure out how to organize. But that's for the second half of the semester, okay? So now we can do this with a linear classifier. Logistic regression is a linear classifier. It's linear because you see that everything is a function of this progress of all the coefficients and the features. So it's a linear combination of the features that we're using there. But it can happen that we have something that is not linearly separable. And so if we use logistic regression, we get a linear separation, but there will be some errors. So in this case, this blue point was left on the wrong side, and we cannot separate the training set with this kind of classifier. So using a linear classifier here. But we saw that there is a trick we can do. We can keep the classifier linear, but put everything in higher dimensions following a nonlinear transformation. For example, suppose that we add another feature which is just the product of the first two. These two are two gene activations. We add a third feature that is the product of the two. So we create a matrix which has one more column, and we copy the original matrix to the first set of columns, and then at the end we put the product of the first two columns. Note that these are automatically vectorized by NumPy. So this is from this matrix all the rows and the last column. And this would be the first column of the matrix, so all rows first column, multiplied by all rows second column. These are two vectors of the same length, so all the products are done in order. And then we get a new vector that is placed in that matrix. So you can do these kind of manipulations easily using these methods. So now we do again a logistic regression, but in this case I'm not going to do everything by hand. I'm going to do like you will regularly do in the tutorials, which is to use logistic regression, the logistic regression class from the scikit-learn. And then we create an object from this class. I'm going to talk next week about this parameter, but this is a regularization parameter. If we use a very high value, it means hardly no regularization at all. If we use smaller values, then regularization is stronger. This is just to tell when to stop, the tolerance for the minimization. And now we call the fit method by giving the features, so the x values, and the values to predict, which is the y values, the y values there. So this is always the same thing. You create an object and you call fit with the data to fit the model. And this is how we can visualize what we did here. So we had this data set, but when we add an extra feature by multiplying these points, we will curve this surface, because now we're doing a nonlinear transformation. So now the data points are in a slightly curved surface in 3D. If we do a linear classification now in 3D, we can cut with a straight plane across that curved surface, and if we project the intersection of the two into the surface, the intersection is now slightly curved here. So this is the same idea. We are still using a linear classifier, a logistic regression, but we change from 2 dimensions to 3 with a nonlinear transformation, and we bend the way our data is spread. It's now in a curved surface. So we can cut it straight, and we cause a curved cut there. Yeah?
I just want to make sure that we're actually changing the points. You want to Z values for the points.
Yes.
Are we doing that?
We,
the one plane to start with, but then you shift that.
Yeah, I added a new feature which was the product of the other two. It could be one of them squared or something like that. But the data set. Yeah. I'm not adding new information because it's just the product of the two there. But the product is not linear. It's a nonlinear transformation. So this is the important point. Note that suppose that we had a feature that was just a linear combination of the other two. We would change to 3 dimensions, but all the points would be in a straight plane also, because we were doing a linear transformation and everything would be straight. In that case, it gives us no advantage, because now if we cut with a straight line, we have the same problem. The trick is that we are doing a transformation that is nonlinear, and so our data is now occupying a curved surface in higher dimensions. And that means that we can cut, yes, this shape here, and that's why we can cut like this. Of course, we can go to higher dimensions still. I cannot do the plot in 4D, but we can add more features. For example, suppose we also add x squared and x1 squared and x2 squared. Now we have 5 features, so this is a more curved surface in 5 dimensions, and now we cut with a hyperplane in 5 dimensions, and when we project back, we have this discriminant here. And we can keep increasing this for, say, 7 dimensions and so on, 9 features. Now, I don't know if you can see there is a bit of red over there. So when we start increasing too much the number of features, you can imagine that now we are in 9 dimensions with a very twisted surface where all our points are spread out. We cut straight, but then things get a bit weird. And now our hypothesis is predicting that a point that falls there will be on the red class, will be a tumor. This is clearly overfitting because it makes no sense that a point over there would not be part of the blue class. But this is what happens when we increase too much the power of the model. It's the same thing we saw last week for regression, but now we're seeing it in classification. We can use a linear model, but using nonlinear transformations.
Change or choose specific surfaces to feed our data, or?
Yes, so basically we're going to talk about more about that next week, so I'm going to finish briefly, but the idea is the same. We can do 2 things. We can select the best model in this case, so note that as we increase the dimensions, we are actually changing the hypothesis class that we're using, because a hyperplane in higher dimensions is different from one in low dimensions. But we can use validation to try to select the best one. So keep some points outside the training set and check for overfitting. Or we can do regularization. We can use a model that is overfitting, but constrain it to avoid strange things like this and try to keep the surface simple. We're going to see that next week. So next week I'm going to talk a bit more about this validation and model selection regularization, applying to classification, and also with some different tricks. So just to sum up, we saw what is linear separability and the notion of the discriminants. We saw how to do this the wrong way by trying to minimize the quadratic error. So there is a big difference between regression, where we're trying to adjust as best as possible to the data, or classification when we want to split the data into different subsets. But then we saw how we can do this with logistic regression. So logistic regression is called a regression because we are actually computing a regression, but to the probabilities of belonging to a class. And then we use that as a classifier by cutting our data where the probabilities are 50-50. And then we split the data into two subsets. And we saw how we can use this linear classifier for solving non-linearly separable problems by the same trick. Non-linear transformation and then separating in higher dimensions. So the next lecture we're going to see how to solve the overfitting problem in these cases. In the meantime, I recommend reading these sections in Bishop's book.